Hi there, resonance and hybrids. Let's look at benzene. You can draw in two different ways, and the red arrows show from right to the left structure. The blue arrows show from left to the right structure. So that kind of the intuitive idea that this double-headed arrow, you can switch between the two sides, right? Now, these two resonance structures are not existing. It's only on paper. But what is existing is what is in green on your right. The dotted line shows the pi bonds are moving around. So there is no actual double bonds. There is no actual single bonds. What is existing is actually in between double and single. We call the bond order is 1.5 for benzene. Now similarly, ozone has 3 oxygens, and we can simplify double bond oxygen and a single bond oxygen given the number of electrons. We count it in a moment, those numbers, right? But we can draw, again, blue arrow to the right, and also we can switch between these two structures. So that's, yes, we'll go with the red from right to the left, yes. So with this lone pair makes a pi bond, this pi bond opens up to a lone pair. We go to the red arrow direction, and then you get a new lone pair on the single oxygen, and you get a double bond. Yes, that one, it's pi bond, right? So now you can see, you can switch to the blue side or to the red arrow side, right? So again, these two resonance structures are not real. They are on paper, double single bonds clear, so we can push arrows, we can explain bonds, and we can do reactions, right? So the blue arrow shows how to go from left to the right. So the lone pair makes a double bond, and the double bond makes a lone pair, right? Now, what is with the green is the real ozone structure, should be. So it's in between double and single bonds. And so every ozone molecule should look like what is in the right with the dotted line. So the bond order should be 1.5 between the two oxygens, each oxygen, right? Okay, so that's a simplification of hybrid structure, which is real, versus resonance structure, which is on paper, clearly showing double and single bonds, right? Now, this one I'm going to show you side by side how to draw nitrates and carbonates and counting electrons. So because sometimes it's a problem to count the electrons. Look at nitrogen valence is 5 electrons, oxygen valence is 6, but there's 3 oxygen atoms, 3 times 6, and negative charge is 1 extra electron. So the total is 5 plus 18 plus 1, which is 24, right? Similarly, learn side by side always so you can compare. Carbon valence is 4, oxygen valence is 6, there's 3 oxygens, 3 times 6, and 2 negative gives you 2 extra electrons. So total is 24, right? 4 plus 18 plus 2, 24. Okay. Now, so put the nitrogen in the center because frequency is less 1 nitrogen, and each oxygen get 1 bond. Bond is 2 electrons, right? Because it's a covalent bond, 2 electrons. Now, we already spend 6 electrons, right? 6 electrons, so 3 bonds. We at least need 1 bond to connect them, right? So that's the basic idea. Now, let's minus that 6 electrons we spent for the single bonds, and we left with 18 electrons. We know single bond oxygens will have 6 electrons surrounding it as 3 lone pairs. Let's put them, because that's what we have learned, and that's what we're going to practice. So voila, we're done. So now we can see no octet for the nitrogen, but there is oxygen octet for all oxygens. So all oxygens are pretty happy, and nitrogen is not happy. So we can do a very simple thing. In the last video I said, if you need, make a double bond. If you need, make a triple bond. We forced to make a double bond here. The lone pair push into a double bond or a pi bond. So now nitrogen will have an octet. Still oxygen will keep the octet as well. So each oxygen has 2 single and a double bond. and there's a negative sign going outside overall. The reason is two negatives and nitrogen has a positive charge, so therefore one negative, one positive cancels out, right? Okay, let's look at carbonate. So the carbonate, again, central is less frequency carbon, and each oxygen has each single bond, so it's 3 bonds 6 electrons, and then again leftover 18 electrons we spread to each oxygen, 3 lone pairs. Now oxygen has octet again, carbon doesn't. Now we're going to do the same trick. Let's try to make a double bond here. So if it didn't work, we're going to make a triple bond even, or another double bond, right? Now carbon has octet, oxygen has octets, right? Now we are good. Now we can redraw this one. Single bond oxygens will have 6 electrons, so 3 lone pairs, and double bond oxygen will have 2 lone pairs, right? 2 negatives outside showing 2 negatives, so that's the overall charge. So that's how you draw the first structure for resonance structures. So now we can keep drawing other resonance structures for nitrates and carbonates. For practicing, you can try perchlorate, sulfate, phosphate, but these ones will have beyond octet for the central atom. So any questions? Yeah, send a message. We will discuss that later. Now going into the resonance structures. Now what you have to think, you're just going to swap this double bond into each other 2 oxygens. So to the right, to down, to left, right? So keep it simple that way. So first you draw the nitrate ion, and then you swap around the double bond, right? So you get 3 identical, the energy is actually identical, 3 different versions of resonance structures. Everything has a negative 1 charge overall, so we are not practicing anything wrong ions to draw. That's not a good idea, right? We practice what is right. Now all 3 we can hybrid into this one. So now the charge -1 is spread equally, 1/3, 1/3, 1/3 on each oxygen. That's the hybrid structure. So if you have a bottle of nitrate, each nitrate will be look like in the pink, 1/3 negative, not -1 on any oxygen, right? So that's the idea. Now same thing for the carbonate. We draw logically how the carbonate should look like, and we realize 1 double bond and 2 singles for oxygens, and then swap around the double bond. So to the right, to down, to left, right? So same thing, left and right. Look at the similarity, practice a couple of times, and then you put the overall -2 outside the square bracket, and that's the way. Now we can draw the hybrid structure. The resonance structures are equally important, and hybrid structure is the real thing. Now -2 is spread equally around 3 oxygens. That's why -2 divided by 3. So like I said, hybrid structures are the real thing in a reagent bottle, and they are not really double bonds, they're not really single bonds either, right? What is on paper is clear double bonds, clear single bonds, clear charges, and that's just for us to learn and teach and do everything else we do, right? Okay, we will be moving to a bit more organic chemistry basics. So I have this compound, positive charge with double bond. It's a conjugated double bond, a negative charge with conjugated double bond, and I will be drawing benzene or aromatic one too, just to compare. Now this positive charge, the pi bond electron pairs come towards the positive charge, because positive is an empty p orbital, so it will be filled with the 2 electrons coming from the pi bond. So nicely the positive goes to the left side, and the blue arrows show how to go to the left side structure, and the red shows how to go to the right side structure, right? So these 2 are the resonance structures for that. Now if you have negative charge, negative means 2 electrons, it's going to start moving first, so to the red for to go to the right and blue for to go to the left, right? So just notice that positive gets the electrons, negative gives away. So each of these structures can have hybrid. So that means dotted line, not a single bond, not a double bond, but in between. But the positive charge is moving around. And here the negative charge is moving around, not a clear double, not a clear single bond, right? So that's the idea. Now we can look at one or two aromatic structures. What's the difference? Aromatic structures are planar and they are cyclic. So that's why they are special aromatic stability, right? So let's get the nitrobenzene. So we have one negative, one positive on the nitrogen, one negative on the oxygen. If you push this red arrow, the pi bond opens up, and push the pi bond on the oxygen to make a single bond oxygen. So what do I get here? I get nitrogen single bond oxygen here, negative charge, and double bond created, and another negative on the oxygen, and still the positive sits on nitrogen. So now we created a new positive charge, and we did not touch these pi bonds, right? So that stays. Now what I'm trying to show you here is it can go back the blue arrow and go towards from right to the left. So think about the two different colors to go from left to the right, right to the left, right? That's how you kind of make sense of the double-headed arrow. And these structures I'm showing, this one has negative, negative, positive, positive spread around the ion, and here you have one negative, one positive. Therefore lesser charges are major products, more charges are minor products.